Good morning to you all. I would like to take this opportunity to welcome everyone to the new series of online lectures hosted by Bhauthiki, NIT's Physics Association. Bhauthiki is a vibrant community of physics enthusiasts bound together by their passion for physics. Through talks, lectures, and discussions, it serves as a platform to explore the wonders of physics. The events and activities organized by Bhauthiki make physics accessible not just to students but to everyone. As a part of our new online lecture series, today we are honored to host Dr. T.N. Narayanan, a distinguished scientist from Materials and Interfacing Engineering Laboratory, TIFR. His research interests span exciting areas of modern science, including hybrid nanostructures and composites for energy management. Currently, Dr. Narayanan is leading projects on the development of ultra-low density 2D nanomaterial-based circuit design. On behalf of Bhauthiki and NITC, I warmly welcome Dr. Narayanan for this exciting talk session and all participants. I'm sure that his insights will be enlightening for all of us. So, sir.
Okay, thank you very much. Am I audible? Is it good?
Yes, sir.
Okay, so one request from my side is that if there is any audio video issue, please interrupt me and tell me, otherwise I will never know. Uh, thank you very much, first of all, for your invitation to this particular platform. Uh, so, and it's really, exciting for me too to share my, recent thoughts with you. Uh, Basically, as introduced by the speaker, introduced by the host. Uh, my research is mostly centered on working on interfaces, various interfaces. That's why we name our laboratory also in the same manner, materials and interface engineering. So today I would like to talk about uh, kind of recent works what we are doing in this direction, where we think the engineering the interfaces can do a lot of things, particularly in terms of electronics and electrochemical systems. So I name it as interfaces, demons or angels, basically to demonstrate the devilness or the diabolical nature of the interface, as it was rightly pointed by the famous scientist Wolfgang Pauli. um, God made the surface, God made the bulk, the surface was invented by the devil. Basically, it indicates that, uh, but the how difficult to understand the interface or surface or interface of any material, and it's very easy to understand the bulk. And I think in next 1 hour talk, I would like to demonstrate how difficult it is to engineer the interface or the surface of the interface. But if you can really engineer this interface, you can do a lot of energy efficient systems and electronics, um, for particularly for future energy systems. So basically, let me, in the same line, I would like to bring you this point. This schematic is actually one of our recent works. What we have shown here, you have a metal surface, and I have some molecules. Don't care about the molecules. There's some molecule. It has a very interesting application. It has, this concept was we adopted from a biological function of this molecule. This is a sugar molecule, and this is something very special. It's a sugar alcohol molecule, and it has a very specific interaction with the metals, and a very out of various sugar molecules in our plants or in the body, in our human body, this particular sugar molecule interacts with the water in a very very particular manner, and this interaction with the water helps for us to make an energy efficient water electrolyzer, even working in a very low potential, have producing large amount of hydrogen. So I will go to the details of these things. So here what I wanted to tell you is that the water structure disruption of by this molecule was happening only at the interface of the metal and the electrolyte. This particular molecule is not modifying the bulk of the electrolyte. But to know whether this molecule is really doing anything, you need to have probes to monitor the interfaces. That is itself is a challenge. First of all, to understand the physics happening at this interface, I will talk in the coming slides. I'll talk more about what I mean by this interfaces. It's always a few angstrom or few nanometer separation, nanometer width distances, nanometer wide distances. So it's very hard to understand what is happening at this interface. So once you understand what is happening, then only you can engineer it. So this is the kind of interface I am talking about. Before I come to the topic of interfaces and how can we engineer the interfaces, let me talk about Tata Institute of Fundamental Research in general. TFR, I don't know how many of you know, it's a deemed to be university under Department of Atomic Energy. And it was started in 1945 by Homi Jahangir Baba inside the Indian Institute of Science campus, and the same year he moved to the Bombay Colaba campus. And over the years, it actually has several centers. And the latest addition in 2010 is in TIFR Hyderabad, and soon is going to be the largest campus of TIFR. It has several other centers, in various places in India, Bangalore, Pune, Bombay, Hyderabad, etc. So the Hyderabad is the latest addition, and it's going to be the largest one in coming years. So the unique aspect of our research or our research philosophy at the center is we don't have a departmental structure. Though we have representations from all physics, chemistry, biology streams, and now we are moving towards the applied mathematics, we don't have a departmental boundary here. That means that any student in physics can actually do a biology research or with a biology faculty or vice versa. Similarly, a biology faculty can really take a physics or chemistry student, or faculties can talk each other, and something like that is really nicely happening within the system with the departmental structure. So this is the unique about AFR Hyderabad, and students can choose their topic after their basic training is in something else. After that, so in our lab has established almost 12 years back in the AFR Hyderabad, here in Hyderabad, and our interest right from the beginning is on materials. And over the last 6 years, our research interest is mostly on not just materials, but materials at the interfaces. So what I'm talking about here, these interfaces, I briefly gave you a kind of idea what kind of interfaces I'm talking in the first slide. But now let us go more into the topic of interfaces. So if, for example, interfaces are there everywhere. For example, this interface I'm talking about, an electrode, a solid and a liquid interface, right? This is a typically happens in catalysis, for example. This is what the schematic it is shown. So you have a metal surface, and metal surface is actually in a electrolyte. It's in a liquid, and it's actually you are applying an electric field to the interface, to the metal. What will happen? So this is a very age-old problem. In the Faraday has discussed it. Faraday told that electron transfer mass deposited will be equal to the electron transfer. This is famous law as the electron transfer process happening during a reaction. It's called the Faraday process. But when Faraday, in that era, when he actually studied the electron transfer process from an electrode-electrolyte assembly, he actually missed out some point. Before the electron transfer happens, there are something else will happen. So this is nowadays coined as non-Faraday process. What are these non-Faraday process? When you apply a electric field, there are molecular arrangements happen at this interface. So we termed as These things are in the inner Helmholtz outer Helmholtz here. What is the meaning of this inner Helmholtz outer Helmholtz? You will have a potential drop across this junction. Okay, you see, and at the 1 by E potential thing, you see, you define the potential as theta potential, etc. But this potential drop across the junction will happen, and at the bulk electrolyte, and by the electrolyte potential will be same as the bulk electrolyte potential. And at some point, then the whole point is by applying the enough energy, you need to have the phi s is applied equal to the applied potential, so that the electron transfer process happens, etc. But this potential difference is always there, forming a double layer at the interface. And these double layers, depending upon the ions in it, it can be from few angstrom to few nanometers or several angstroms, depending upon the ions present within this layer. Now, so this is the diffuse layer. Inner atmosphere is more tightly packed. Sometimes ion can get specifically absorbed too. Now, what is important? This molecular arrangement happens here during the initial time because it happens very fast, and then the electron transfer Faraday process happen. That's why the Faraday missed this molecular arrangement, and this is called the non-Faraday process. So one of the questions we are asking, many case heterogeneous reactions, these non-Faraday processes are very important, and we not neglect it. So one of the questions we ask in our research, can you control this non-Faraday process? Can you control the molecular arrangements at the interface? And since we are controlling the molecular arrangement, because of this, can you control the Faraday process that is happening after that? This is one of the very interesting questions we asked, and we found that yes, you can have a control over this non-Faraday process, and if that is the case, you can really control the Faraday process, right? Now, so this is one example what I have shown here. I will go to the details of this particular thing later. But what I mean by that, in an aqueous reaction, water based reaction, it's a catalytic process. Let's say hydrogen is being generated from water. You are producing hydrogen using a metal surface like a catalyst surface like gold or platinum. Now the question is, can you control the water arrangements near the electrode surface? If the bulk electrolyte structure hasn't changed much, but in the interface electrolyte water structure means water coordination. In principle, a water can coordinate it, so one molecule of water can coordinate it to four other molecules of water. Now it can actually have an hydrogen bond free system also, or three hydrogen bonds or two hydrogen bonds, etc. Depending upon that, by controlling the number of coordination, your actually energy to release the hydrogen from water also changes. So can you do such changes or not? This is one of the questions we asked, and we found that by adding some small amount of molecules in this particular work, we have shown that adding some dimethyl formamide, you can actually bring a hydrogen bonding at the interface, very selectively at the interface, and the straight hydrogen bond will form a semi-solid like water, and this actually they suppress the hydrogen evolution reaction, hydrogen generation from water, but actually it enhances other proton coupled reactions like a carbon dioxide reduction reaction. So this is a very interesting thing. So what I'm asking here, by making and breaking of hydrogen bonds, you can actually control the reaction, electron transfer reaction, because all these, so I will show you that several of these reactions, heterogeneous electron transfer reaction, why it is called heterogeneous, because electron is transferring from an electrode of metal electrode or solid to a liquid. That is why it is called a heterogeneous electron transfer. So in this heterogeneous electron transfer, thermodynamically, several reactions have similar energy. The free energy is are similar, but by controlling the water structure, can you control the kinetics, and hence can you control the product? So by either by controlling the thermodynamics, or you controlling the kinetics, you can actually change the reactions. So this is one thing where what we have shown. Now, such interfaces are very, very important in various cases. For example, it is also important in batteries. Why it is important in batteries? Because the battery also has an interface. There is so very stable electrode, solid electrolyte interface formation is very, very important. So, for example, what is happening in the battery when you have an anode and cathode? You have an anode and cathode. While charging while the charging process happens, the electrons. So you apply a negative potential to your anode and positive potential to your cathode. So lithium will basically lithium ions where from the cathode, something called the lithium cobalt oxide, and will actually de-intercalated or oxidized, and then it will basically will go to the anode, and with this electron it combines and form an intercalated lithium compound. Now lithium will form an intercalated lithium formed in the case of typical anode like a graphite. It forms a lithium lithiated graphite or lithiated carbon system like LiC6 kind of things. So when you have such a charging process by applying negative terminal of your battery, external battery to your anode of the battery and the cathode, positive to the cathode, you will have after some time, after full charging, you will have a LiC6 and this have a lithium rich cathode. Complete removal of lithium from the cathode is almost impossible. Now, what in that kind of situation, if you look into the energetics of the battery electrodes, you will have such a situation. So this Fermi level of mediated graphite is quite higher than this Fermi level. This, when you connect externally, stop the charging process and externally connect a load, then you will see that the electrons will spontaneously will get transferred. Electrons will get spontaneously transferred from anode to cathode, and similarly lithium will go from the anode to cathode through the electrolyte. So this will complete the circuit. So then the energy levels will become equal. So this is the charging and discharging process. What will happen during this initial charging discharging process, the electron lithium ion shuttling, is that you have electrons, some of the electrolytes get interacted with, I mean, the electrode will get interacted with the electrolyte, and then there will be a solid electrolyte interface formation. And this solid electrolyte interface will have a different composites, different organic, inorganic materials, and this optimized organic, inorganic mixture interface will stabilize the anode and cathode for the electron transfer process, or make the electrolyte stable. What I mean by that is that if you don't have such a stable solid electrolyte interface, then you can actually have the electrode can interact with the electrolyte continuously. It will degrade the electrolyte, and thereby basically your electrolyte will be completely used up by the electron transfer process. But this solid electrolyte interface will allow a lithium transport across the junction, but at the same time it will not allow the electron to transfer. So there won't be any electron transfer across the this particular solid electrolyte interface. And this is very important to establish a solid electrolyte interface. Now most of the battery problems are due to this absence of a solid electrolyte interface, because a solid electrolyte interface, we cannot externally make the solid electrolyte interface and do it, because if you do it externally, then the thickness matters. If you have a very high thick solid electrolyte interface, then the ion transfer itself will become a problem. But if you are and the components, as I told you, it has a mixture of components. So putting a real actual component at the interface which will be conducive for lithium ion transport will be very difficult to identify, because depending upon the system, depending upon the electrolyte, depending upon the electrode, this interface, the components of the interface can be different. For example, now people are looking to develop a stable solid electrolyte interface. For example, in our one of our recent works for both for solid state batteries and liquid batteries, what we found is that if you modify your separator with a something called a fluorographite, it's a very large area possible method, and then you use this separator instead of normal separator, because anode and cathode need to be separated. Otherwise, what is the problem is that they will be in contact, and then they can get shorted. Now if you use this thing, what we found is that this separator material what we use, it's a fluorine and carbon containing material, will interact with lithium and form a very nice uniform lithium fluoride interface. And this lithium fluoride interface will basically help for not forming dendritic lithium deposition, even if you shuttle back and forth lithium very fast, right? Because if you do in a very slow farm, in otherwise, if you do in a very fast charging and discharging, that is almost always required for a battery, then what will happen is that you will have a non-uniform deposition of lithium, and hence you will have dendritic deposition and the battery will get shorter. So this is one of the problems in the current battery industry. People are looking for fast charging. You might have heard that the Tesla is coming up with the batteries having 5 minutes charge, 5 minutes discharge, etc. Why we are all talking about such a fast charge discharge system? Because the power density, the fast charging and discharging is a measure of power density of a battery, of an energy system in general. You need to compete with the petrol and diesel, the power density. Energy density, we need to compete with petrol and diesel, since we are talking about replacing petrol and diesel with batteries. So in that case, you need to talk about fast charging, discharging systems along with a high energy density system. So people are talking about lithium metal based batteries, so that the energy density can be 10 times higher than the current lithium ion batteries. At the same time, you can have a fast charging and discharging, so that you don't need to worry about, you need to wait for very several hours to charge your battery. That is our current case with the current car batteries and all. You need to charge for several hours, particularly with the AC chargers. So now we address this issue. We try to address this issue by modifying. Now you may ask the questions. Now we knew that the material which is helping for lithium ion transport is lithium fluoride. We know a priori now, because we studied it and we knew that it. And very, not only us, various people have understood that it's a lithium fluoride. Can you deposit lithium fluoride? Because lithium fluoride is a well-known material in photovoltaic. They use the same lithium fluoride deposition in solar cells, etc. Now, can I use the same lithium fluoride a priori before you make the electrode? It is not possible, because the thickness of the lithium fluoride needs to be in situ form. If you do a high lithium fluoride deposition, the polarization will happen. The ions will not go through the interface. That will have actually, because the lithium fluoride is an electronic insulator. That will happen. That will polarization will happen. Then huge resistance will happen, and the battery will not function properly. So this has to be formed in situ. This is the importance of interface. Now, I discussed about solid liquid interfaces, where the potential will be generated and at the interface, and this potential and the field are very important. I hope you got this point. Now, if I could look into a solid interface, as I think many of you are from the physics background, this might be more interesting to you, because solid interface is very similar to solid liquid interface. What is the similarity here? Because particularly if you look into metal semiconductor junction, and this, metal semiconductor junctions are for investigation right from the beginning of 1947, when a transistor was invented. Because this is one of the problems in the transistor development also. Because when you have an interjunction of metal and semiconductor, depending upon the work function of the metal, and semiconductor can be an n-type or p-type semiconductor, and the n-type semiconductor electron affinity, or the p-type semiconductor the ionization potential. Depending upon that, you can, when you form a junction, there can be a depletion barrier formed at the interface. Why it is happening? For example, if you have a metal work function and metal having some work function, and you have a semiconductor, let's say an n-type material, having a very low work function or ionization potential. Then what will happen is that when you form an interface, the its conduction Fermi level is above what is that of metal. So electron will get diffused. It will form a barrier at the a potential barrier at the semiconductor junction like this, because the electron get diffused from the semiconductor at the interface. Bulk will be, so when you form a junction, Fermi level will become even, but at the interface there will be a potential drop. Now what will happen if you try to inject electrons through this particular system? Electron has to cross a barrier. There's an energy barrier, the potential barrier is there. And this, according to the Short-Schottky relation, the Schottky barrier height is phi m, work function of metal minus electron affinity, or the electron affinity or ionization potential, depending on whether it's a n-type material or p-type material. And this is same with the hole also. This is for an n-type material, that's why I said chi electron. So now the thing is that so you can that in principle the electron has to climb this barrier and cross it. You know, the electron can also tunnel through it. But if the semiconductor is not very heavily doped, this thickness will be quite high, because as a spatial width of this diffusion barrier will be quite high, because to compensate the charge in this particular junction, you might use a large amount of electrons at the semiconductor junction. So the spatial width of this barrier will be quite high. Then the electrons cannot able to tunnel through the barrier and cross this semiconductor to have the transfer. So the field emission will be quite poor. Thermal and thermionic emission will be already happening. So you need to climb the barrier, and this is a real barrier for an electronic device, and that actually causes heat dissipation in the device. When you talk about spintronic devices, this is even worse. If you have such a Schottky barrier, you will have the spins will get relaxed. So this is another very major problem here. So electronics and spintronics, the Schottky barrier is one of the major concerns here. Now you may ask the question. So is it an issue in a silicon semiconductor? It's already been matured. Silicon semiconductor technology has been matured. It is an issue, but there are ways they address this issue in a bulk semiconductor. So the thumb rule for a Schottky and ohmic contact. So this is again a textbook things many of you might have already studied. An n-type material is an n-type semiconductor. The materials should have a lower work function. The metal should have a lower work function. For example, an MOS2 is a semiconductor having a work function of 4.8. So if you use a gold contact, it will have a Schottky barrier. But if you use a titanium contact, it will be having a ohmic contact. So you really need an ohmic contact here. Similarly, any semiconductor, this thumb rule will be similarly exactly the opposite the p-type semiconductor, which is a p-type semiconductor. A higher work function metal should be needed to be used, because the hole is the major transporting. The energy bending will be that. So this is a thumb rule for an entire semiconductor. You need to use a lower work function metal to form an ohmic contact junction. Now, how do you address this thing in a silicon semiconductor? So silicon, to address this issue, what people do is that before the silicon metal contact formation, they at the junction they do an ion implantation or so to make it a degenerate semiconductor. So basically, what you mean by degenerate semiconductor with a heavily doped junction, you are actually bringing down the barrier, the tunneling barrier, so that tunneling will be easier, so that you can actually ensure a flat band near the metal semiconductor junction, and then you can have a very feasible electron transfer from the metal to semiconductor. So this is the way the bulk semiconductor industry works, and where they do a very nice contact with the metal and semiconductor to address the Schottky barrier junction. Now let's come to when we are moving towards the advanced technology. What is the issue? Now we know that MOSFET scaling is happening Moore's law. Everybody are well aware of Moore's law, etc. As you go down, so initially this length scale used to represent the channel length of a transistor, but now no more. this doesn't have any channel correlation with the channel length. But we are talking about, Samsung is talking about 2 nanometer, the Taiwan-based company, they are talking about 1 nanometer technology, etc. Thus, we are scaling down, basically bringing the device transistor dimensions lower and lower. Though when we are bringing lower and lower, then the conventional semiconductors become use of the conventional semiconductors become very difficult. There we need to talk about the semiconductors which are ultra thin by dimension. This is called the two-dimensional semiconductors, like the transition metal dichalcogenides. Unlike silicon, silicon has a thermodynamic stability issue below 2 nanometer. So it's not stable. So you cannot use them for modern technology for silicon. Yes, by different geometry. That's why people are talking about new kinds of transistor geometries, FinFET, all gate all around transistors, etc. With the silicon, various things are done. But most of the time, particularly for low power electronics, people are talking about ultra thin semiconductors as a good choice because the electrons, the carrier are massive in these 2D semiconductors,
Maybe you are in chat.
and they are quite.
I slept at 9:30 p.m. Okay.
Can I continue? Hello, hello,
Yes, sir.
hello. Yeah, so sorry, in between I heard someone, so I thought there's some issue with the audio. Okay, anyway. So people are talking about ultra thin semiconductors. Now, particularly when you talk about ultra thin semiconductors, a class of family called transition metal dichalcogenides are receiving very high attention and interest. So, what are these transition metal dichalcogenides? So, transition metals, we all know what is a transition metal. Certain transition metals with the chalcogen family, that is oxygen family, can form two-dimensional materials. Two-dimensional materials, and they form in bulk. And then you can actually brought into monolayers. Monolayers in the sense of the order of less than 1 nanometer. And these kinds of act like a very nice semiconductors having a reasonable band gap, and they are thermodynamically stable also. So particularly, some of these metals, some of the chalcogens are layered, but others are in non-layered chalcogens. But most of these metals, these hard-colored metals, actually form nice layered structures with the chalcogens like sulfur, selenium, and tellurium. Now, what is this? So they form in bulk, but with a van der Waals gap. And van der Waals gap is typically, as you know, in graphite, it is around 3 angstrom, and then it can go to 6 angstrom like that. And as the van der Waals, since there is a van der Waals gap here, you can actually take one layer out of other. And one layer means actually it's a tri-layer system with two layers of chalcogen, where one middle layer is with a metal. So this is, so for example, if it is a molybdenum disulfide I'm talking about, that's why I'm going to talk more in this talk. You have a molybdenum layer on the middle and two chalcogen layers. Now, if you look into this thing, so molybdenum, single layer molybdenum disulfide, etc., were known to the field before even the extensive discussion and research happened on graphene. Even we can see very old papers, and molybdenum disulfide is quite this chalcogen, as the name suggests, they are quite stable. Most of the ores are available, of these metals are available in this chalcogen form. So they are actually quite stable materials. So, and people were using them for catalysis, particularly in oil industry, etc. So they are quite known as a stable material. Now, when you go to monolayer system, so that if you look into just one single layer, actually the arrangements of atoms are like this. You see, this is a molybdenum layer, and as I mentioned, the yellows are the chalcogen layers. So the most stable form, the chalcogen, the top layer of chalcogen sit on top of the other below chalcogen. So you can see this is one layer as the one chalcogen sitting exactly on top of the other chalcogen layer. Middle there is of course a molybdenum layer is there. So this is like a trigonal prismatic geometry with a D3H symmetry. But You can also, with some certain strain, you can actually rotate, slide the top sulfur layer, and it can actually form an octahedral or trigonal antiprosymmetric point group with OH, also with a D3D symmetry. Now in this thing, so that interesting aspect, just by sliding this sulfur layer one over the other layer, you can actually undergo a phase transition from a metallic to semiconducting to metallic. And this is a reversible phase transition from to a metallic to semiconducting to metallic and back. Now, how do I identify? There are various ways. Both of them have a very, very specific phonon modes, which are very sensitive to their phase. So you can actually look into Raman spectrum, Raman analysis to see whether whether which phase it is being formed or so. Or the electron microscope you can see. Because you see here, as I mentioned, if you turn the two sulfur layers on top of each other, here one sulfur layer is not on top of the other sulfur layer. So this is called 1H MOS2. As I am going to talk more on this today's talk. And this is called 1P or 1P prime MOS2, which is actually a distorted octahedron. So this sulfur layer is not on top of this thing. Sulfur is less atomic number than MO, and in the transmission electron microscope, particularly if you look into the diffracted image, you know that contrast is completely depending upon the atomic number of the material. So sulfur, it is a very weak, very low atomic number. You will not see the sulfur column if both the sulfurs are not in the same line. So you think that you are looking from the top, and then you are seeing the transmitted of a monolayer system. So whatever you are seeing will be exactly like what it is arranged, what it is arranged in a plane, right? Now, if so, since in the one next case, both the sulfurs are on one top of other, you will see a sulfur column there. But and molybdenum column, both the columns will be visible. But in this case, the 1T phase, since one column is missing because the one sulfur is only there in the one column, sulfur column will not be visible. So only three things corresponding to the molybdenum sites are visible. So in this way, you can easily look into the transmission electron microscope, particularly scanning transmission electron microscope in dark field imaging. You can see whether this is a 2H phase or 1H phase or 1T phase. Why it is 1H? It is called one layer hexagonal. 1T is in one layer tetragonal or so. So this is the way it is. You name 1H or 1T. One is semiconducting and one is metallic. Now I'm talking about a level where I can do a precision engineering, right? So here I said like I will get monolayer by peeling off one layer over the other. Typically in the lab we don't do peel off. I'll tell you how we are synthesizing. Now what I'm trying to say is that I can even replace one molybdenum or with another element. Either it can be like a chromium or it can be like a vanadium, and we can actually see them whether it is getting replaced or not. There are various ways to see it. Now, what is the advantage here is that chromium and vanadium, you can actually engineer the band structure very nicely. So not only for as a semiconductor, which is electronics, by doing such kind of precision engineering of elemental replacement, you can actually do them useful for them for valleytronics too. Valleytronics is another emerging field in data storage, etc., where you can control the band valleys. Band valleys means the valence band, higher energies of the valence band or lower energies of conduction band. Can you control these values alone very nicely? And we found that in the recent work, we found that you can actually control the values by choosing the right transition metal, replacing the position of MO in a very small amount, and then that way you can engineer the values. So the electronic properties that is brought by this chromium and vanadium are similar, but the valleytronics part are different. So this is quite nice. So you can engineer the electronics independently, valleytronics independently, etc. It's bringing a lot of opportunities to use this material for beyond electronics too. Now, why MOS2? I told you MOS2 is one of that very, very stable semiconductor, and it's a two-dimensional material around 0.8 nanometer, less than 1 angstrom.
sorry, less than 1 nanometer. And semiconductor band gap is around 1.8 electron volt. It's quite stable. It can form heterostructures. By doping, we found that it can bring room temperature magnetism. It is acting like a good catalyst, as I told you. Hydrogen, recently people have showed that it is a good hydrogen evolution reaction catalyst, but no, historically it is known for hydrodesulfurization reaction in petrochemical industry. People are using these materials. Now it can be used for battery. I will show you one application, and then this is, I mean, there are various fundamental interests too. Now, let me talk about this metal TMD junction. That the interface is of interest, right? Now, in a metal semiconductor junction, I told you, um, in a bulk, how in silicon, how are they addressing this issue? But in a typical metal with a semiconductor, the metal will, you give a potential to the metal and the electrons will injected to the semiconductor. So you can have actually different barriers here. One is that there can be a physical barrier between metal and semiconductor. Though you are depositing physical deposition of metal, right? Either using thermal vapor deposition or sputtering, you are depositing a metal on top of a semiconductor. Doesn't mean that most of the time, not always, most of the time doesn't mean there is a covalent linkage between metal and semiconductor. So this is actually a transmission electron microscopic image, a cross-sectional image of a metal semiconductor junction, gold MOS2 junction. There is a gap of around 3 angstrom or around approximately 3 angstrom. So this is a very ultra thin neat interface. For example, in our recent study, we found that this gap can be even higher. You see a metal semiconductor junction. So there is a real gap. There is no covalent linkage between them. So you can actually, there is a gap here, right? Now, this is physical gap. Then I told you about the metal work function and the MOS2 work function can be different. This also can be energy gap also. So there is a physical gap and energy gap, both need to be addressed in this thing. And this junction is quite nice because this is the same semiconductor we are talking about. Now, how to address it when you create a channel of this one? Now, this is a big question, right? So we can have a very weak adhesion, or we can actually have a partial overlapping, because if there is a negligible tunneling. So partial overlapping means, the physical barrier can be minimum, but at the same time, you will have an interaction with the metal and the defects in the semiconductor. Why the defect in the semiconductor? So I told you about the Mott-Schottky barrier, and very nicely you can choose the semiconductor or the metal by looking into their work function. These are ideal cases where the barrier phi SB follow phi M minus chi is a very ideal case. Many cases, if there is a defect in the semiconductor, the metal site will get pinned into a particular defect site. So even if you vary the metal, then this will not follow the phi SB equal to phi M minus chi. So there won't be any kind of relation like this. So it will be a problem. So this is most of the cases, semiconductor without defect is quite hard to develop. And this is the case with the two-dimensional materials also. There can be several types of defects in it. It can be of sulfur vacancies in MOS2. It can be of molybdenum vacancy depending upon the synthesis strategy you are following. So this defect level, if it get pinned, then the Mott-Schottky barrier, the relation will also not be followed. So then so you cannot directly choose the metal like that. So you need to have, so this is what I said, partial orbital overlapping is because of the Fermi level pinning. If you actually end up pinned, the energy levels get pinned into certain energy levels. Now, what you need is that you need to have a very, very strong hybridization with the semiconductor and the metal, so that there won't be any energy gap between the metal and semiconductor. So and then the Schottky barrier will be only decided by the phi M minus phi chi relation. So you need to have a good interaction with the metal and semiconductor. Very orbitals, the real orbital interaction needs to be there, and strong hybridization with the induced metallization should happen at the interface. So the physical gap should be very, very minimal. At the same time, the energy of they also need to be interacted each other. The orbitals also need to be interacted each other so that they will have a very, very strong binding. How do you actually accept? So the top layer coating, if you have a monolayer coating a metal on top of it, like as I showed here or here, will not work because there will be a physical gap. So you need to deposit from the side. The metal needs to be deposited from the side. What is the advantage here? At the side, as all of us know, the side will have lots of dangling bonds. This end will have unsaturated bonds. So these unsaturated bonds will help for interaction with the metals, and we will form a very, very strong hybridized orbitals with the metal states, and it will help for better electron transfer. Now, this is, but not the most of the time it's very, very difficult to create such a metal coating in industrial level. So creating such junctions, contacts is very difficult. So that is why the contact engineering is a very problematic issue in the electronic industry nowadays. And CMOS compatible interface engineering approaches what these people are looking for, and this is one of the limiting factors why 2D materials are still not into the market, or why the growth of the 2D materials coming into the market is limited, is only because of the interface engineering. Now, how do you do growth? So we can do growth of such very nice TMDs, transition metal dichalcogenides of various kinds in lab using chemical vapor deposition. You can control the thermodynamics and kinetics. You can and control the nature of the crystal, etc. So this is an MOS2 monolayer crystal, and this is the same monolayer crystal you can engineer by controlling the molybdenum to sulfur ratio during the growth. And not only that, some of the sulfur can be replaced with the selenium in a very, very selective manner, so that molybdenum selenide, sulfur is completely replaced with the selenide, is again a semiconductor having a 1.5 electron volt, but molybdenum disulfide is a material which is having around 1.89 electron volt. So we showed that you can actually control the band gap in a very controllable manner. It's in monolayer limit, that also you need to think about. From sulfide to selenide, a very controllable manner, so that you can actually have a variety of semiconductors, monolayer semiconductors by this fashion. And you can do further and control. You can also create Janus structures. We recently, we are actually quite successful in making such Janus structures. What is Janus? Janus are actually, two-headed, two-headed Janus TMDs are two-headed systems. That means the top layer is selenium or bottom layer is sulfur, or the other way. So one layer, so the typical molybdenum disulfide or selenide, both the layers are sulfide or selenide. But here in one top layer is completely converted to sulfide, the other layer is completely converted to selenide. So such structures can also be developed, and they have very quite interesting thing, because an induced dipole moment will automatically come into this picture, because sulfur and selenium have two different electronegativities. So this will create a lot more interesting things, both electronically and electrochemically. So I'm not going to the details of that, but you can actually have such control over it. Now, lab level. Now, the question is that whether you can get in larger level or not, right? So, CVD method is not a very nice way to create a large area crystals in the lab. So, wafer level synthesis, you need to do metal organic CVD or so, and we can actually create large area molybdenum disulfides on wafer scale MOS2 or any chalcogenides, or you can even control the continued growth in a vertical manner. You can arrange them vertical manner, horizontal manner, etc. in the lab. I mean, they have a lot of interesting applications depending upon this, because, for example, these vertically arranged systems can have applications in catalysis. So, or in the large area monolayers can have applications in optics and electronics, etc. So, what I'm trying to convey you here is that you can control the area, you can control the nature, you can control the quality, etc. But now, when you talk about new materials, and I told you the defect is inevitable, right? It's very, very difficult. And this is not only true, I mean, not only the issue with the monolayer 2D materials of TMDs or graphene or whatever system. It is the issue with all new materials, even perovskite, when people are talking about defect is one of the major problems. Defect density is of the order of 10 to 12 defects per centimeter square. But when you talk about monocrystalline silicon, etc., 10 to 12 per centimeter cube or lower. So defects are quite high, and different types of defects is one of the problems. Now people are trying to make low defect systems. So this can be of difference because when we identify the nature of the defects, it can be selenium vacancy, sulfur vacancy, selenium vacancy, clusters, etc. Various kinds of defects can be there, and this defect actually will be a very big issue in the when you use them for applications. But now recently we could show that we can actually create nice, high quality, less defective system, large area in CBD. And when you do, and you can do not only this, another problem here is that when you grow such TNDs, many times you need to transfer them into another substrate. Because even if you grow on a transition metal like chalcodone semiconductor on a silicon substrate, silicon wafer, because that's a silicon dioxide is a semiconductor, so you may think that it can be directly used for electronic application. But no, adhesion will be quite poor. So then you need to transfer them into a very nice another substrate. This is another problem with the semiconductor, such 2D TMDs. Not graphene, it is an issue. Graphene it is much more worse because graphene most of the time grows on a metal surface. So then the transfer into another semiconductor is very, very important. In that transfer, there are lots of polymer residues can happen because this single step, there is a very hard to optimize a single step method, but you need to have a multi-step method in introducing a lot of chemicals in this transfer method. So optimizing a single method is very difficult. But still, we could optimize a method which can actually transfer quite neat transfer with a less issues to the transfer films, less issues in the sense of less defect formation while transferring. And how do I know after the clean transfer, it's a multi-step process, and even do a long exposure of ethanol, which will actually remove all the polymer residues. So when you do after all these things a clean MOS2 surface, you can see there's no contrast difference almost everywhere. It's a uniform contrast, indicating that's a nice hexagonal crystals being formed. Now, when you do these things, then the immediate thing, how do you judge the physical properties, how the quality of the crystal by doing the transport properties, the FPT characteristics. I'm sure you are aware of the field defect transistor, how you construct and how do you do the transistor analysis, transistor characteristics, particularly gate VGS versus IDS. And I mean, just to bring you into the point that it's not what we are talking about something not happening another 50 years time, but already people are talking about the commercialization of such transistors. So we are talking about something commercially feasible. That also you need to understand. So what we found is that in terms of semiconductor metric, the quality, the on-off ratio is quite high, and the performance is quite nice, but this performance is coming with a titanium contact. So titanium MOS2 contact will exhibit a remarkable on-off ratio, high carrier mobility, high carrier density, and with a silicon dioxide, a reasonably good mobility too. Because the mobility of the material, the carrier will completely depending upon the carrier, the dielectric you use. So basically, it's also quite nice. Now the problem here is that titanium is not a good contact for electronics because titanium will most of the time will interact with the semiconductor. It can diffuse, it can oxidize. Titanium oxide will form several issues will be happening with the titanium contact. So if people really looking for a gold contact, the moment you bring a gold contact, and when you calculate the Schottky barrier height, it is found that around 215 MeV. 215 MeV is quite above the room temperature, 25 MeV. So it means that you have a quite high barrier to overcome for electron probe transfer. So the moment you bring into a gold contact the performance, you will not get such a performance. So that's what I say. Means a high quality semiconducting material with just with the contact, you can see the poor performance because the contact is important. Now, question is how do you bring a good contact? And no metals. People have tried with the graphene contacts. Graphene is a very good semiconductor metal. It will I do the same metallization at the interface, but the graphene in contact with the metal will break the junction. So this will be a problem. So graphene contact will not work for particularly when you want to acquire long-standing performance from electronic device. People have tried indium, gallium, etc., but indium, gallium will not be compatible for CMOS technology because it does in high temperature. So then wafer processing will not be possible. Now we are looking for a semiconductor which is stable at that temperature. At the same time, it is semi-metallic, and it forms a nice van der Waals junction between the metal two semiconductors. Right now, we are looking for such a semiconductor, and we found that you can actually tune the conductivity of MOS2. MOS2, as I mentioned, it's a semiconductor, but we found that it can control the electronic conductivity of the MOS2 semiconductor by doping with certain elements like vanadium. And initially it was an N-type semiconductor, and as you increase the doping level, it actually from N-type it becomes a P-type semiconductor, and then further enhancing the doping, it will become a degenerate semiconductor. What I mean by degenerate semiconductor, I'm sure from the transistor characteristics, what I mean by that, gate voltage independent of gate voltage. So it become a degenerate semiconductor. So it's not a metallic, but a metal-like, and conductivity is 7 orders enhanced. Now the interesting property is that when we bring this contact to the metal semiconductor, so to the MOS2 gold contact, we could bring down the barrier into approximately 99 MeV. So 250 MeV to 99 MeV, and it's quite stable also. Even at high temperature, it's quite stable. We have done this experiment around 200 degrees Celsius. It's quite stable, this interface. And bringing down with these kinds of two-dimensional materials is quite interesting, and it can be really, really scalable. And we showed that actually we can do a very nice patterning with these two semiconductors. So you have a gold with a degenerately doped MOS2 with a semiconductor MOS2. So this junction will work as a low contact junction for MOS2 transistors, which can perform as good as a titanium based contact. But titanium contact will not be useful because titanium long-term stability will be a question. So this is one aspect of interface engineering. I hope I could convey you that how important interface engineering is. Now, if you give me another 10 minutes, I would like to talk about a few things. Do I have another 10 minutes? Can I take another 10 minutes?
Of course, sir.
Okay. Now, one question is stability. As I told you, defects are prone in these two-dimensional materials. And the problem with the defect is that as the defects will interact with oxygen, etc., in the environment, the material can get degraded. For example, a hard probe, a MOS2 device, a hard probe geometry. We are just keeping this device in a ambient environment, and we found that it's actually got degraded. And when we looked into this degradation, it is actually coming from the edge, because that's edges, as I mentioned, it's highly reactive. Now the problem here is that can you protect them by any other layer? We found that you can actually protect them with a graphene. But again, I told you graphene needs to be grown in another substrate. You need to do a transfer, etc. A lot of things. Then this makes it's almost impossible for a technology. Now, what we showed is that we can actually address this issue by some other kind of carbon deposition. So we could do an in situ carbon. It's a kind of amorphous carbon layer. We call it the fluorographene layer. It's a disordered carbon. It's an ultra thin disordered carbon. It has very, very interesting properties like a very nice ion transport, etc. But I'm not going to that, but you see, just after the growth, this membrane can be grown on wafer scale on top of the MOS2 itself. As I said, the MOS2 is get protected here. So this can be done immediately after the MOS2 growth without even exposing the MOS2 into the environment. So this is nicely protected, and then you can actually transfer them. So you can see both the graphene Raman modes and the MOS2 Raman modes in the, if you take a Raman, and then you can transfer the same transfer methods of liquid transfer methods for these bilayer system also MOS2 and graphene, and you can see they are actually nicely bonded each other. So you can do them, transfer them as an individual layers. Sorry, as a hybrid layer itself. Now, when I do this study, the first thing, MOS2 as a semiconductor, you will be using silicon as a photo detector, right? So it can absorb light and form electrons and holes, and electron can be detected, and this will be a nice photo detector. Now we use the same photo detector concept here with this MOS2 interface. So it has lots of synergistic effect. Let me not go into the synergistic effect, but I would like to convey you that how important the interface is. That I used a material called fluorographene and MS, where the molybdenum disulfide is a single layer of molybdenum disulfide. Since it cannot be alone used because of stability issue, it's alone is a nice photo detector, but when you use the FG in combination with the MS, in this first red case, I grown a MOS2, and then another transferred another fluorographene layer on top of it, and by transfer method. But this black one, what I did here is that, we in situ grow a layer on the FG on MOS. So in principle, red and black are of same material, but the two different ways the transfer happen, right? One is in situ growth, and then in the red one, it is not. It's a layer transfer method. Now you see the performance, photoresponsivity of these two devices are quite drastically different, right? This is what I told you, right? The same material can protect the molybdenum bisulfide, but how you transfer is important, because all these differences coming from the interface, because during the transfer I told you there can be lots of contaminants can come, and these contaminants actually will actually deteriorate the performance of the device and affected the performance of the photo detector you developed. So this is why I said, choosing the material is not only important, but also it's important that how do you make this interface is important. This is what I told you. If you know how to play with the interface, you can actually make it is of more like God like than devil like. Now, it's quite stable. This MOS2, as I told you, it get degraded, but even this can be heated at 200 degrees Celsius, water treated, etc. Nothing will happen to the device. Now, in brief, I will just in another 3 minutes, I'll show you one of the other very interesting aspects what I have done. So I hope I could convey you that how important the interfaces are. Now, knowing these interfaces will help you to propose new devices and strategies, right? For example, you are aware of solar cells. You are all aware of batteries. And what we are currently using, coupling a solar cell with a battery. Problem with the coupling a solar cell with battery is that you have lots of interfaces, and I'm sorry, because in terms of converters, rectifiers, etc. And the problem with all these converters and rectifiers is that you will basically lose the energy, the efficiency, the solar to grid conversion and the battery is actually depending upon the efficiencies of individual efficiencies of all these kind of interconnecting devices. So even you have a solar cell of 26% and the battery of more than 80% efficiency, the coupled system will not have that efficiency because you have lots of losses as the coupling couplers. Now the thing is that we ask a question: can you directly charge a battery using sunlight? So we found that this concept has been people have used, for example, in Weizmann, David Cohen, And Gary Hoods in 1976 actually proposed such a direct electrochemical energy storage mechanism using sulfur SS2 minus system, electrochemical system, but very poor performance. And then this problem was revisited by people in 2017, where they said that a battery can be coupled with organic dye. Organic dye will electron holes separation will happen when it absorbs light, and these holes can be used to de-intercalate the lithium from, let's say, for example, lithium iron phosphate, and then the electron can be used externally for charging the purpose. This was a proposal because these dyes, organic dyes, are not stable in these electrolytes what in a battery uses. So they could not actually prove the mechanism, but they just show that some kind of charging things happen. Not even know what exactly is happening. This was again probably looked into by organic system where the exciton formation, electron hole formation happens in the same system. The intercalation happens, but again organic material, same issue happens. Why? Because organic materials are not stable in organic electrolytes. Now we looked into the problem slightly different manner. We asked the question. So what are the questions we are asking here? So I told you the functioning of a battery in the previous slide, right? In a battery, while charging, you apply a negative potential to your anode and positive to the cathode, and you are pushing the lithium ions from cathode, let's say lithium cobalt oxide, to anode like graphite, and electrons will be supplied here. So they will form an intercalated graphite having higher energy work function Fermi level. And when you have full conversion of lithium from here to here, cathode to anode, it will be fully charged. And then when you connect through load, externally connect through load, spontaneous discharge will happen, because since both the energy, anode and cathode energy will become equal, right? This is the way it happens. Now the question is that, can you do the same mechanism by the light or not? So you need the light window at the cathode, right? So cathode, you need to push the lithium ions and give the electrons to the anode. So this is the way. So you created a window at the thing, a photocathode. You need a photocathode to be used. And in this photocathode, exactly like when the light falls on, the holes have to be generated, and the holes should actually push the lithium ions through the electrolyte, and the electrons need to go through the external circuit and react at the anode to form the lithium intercalated graphite. This has to happen. Now we asked the question, right? Can you do a semiconductor heterostructure for this thing? Because semiconductor heterostructures are known for their stability. But there are quite a number of challenges here. This semiconductor heterostructure, you cannot do a layer by layer transfer like a semiconductor in the photovoltaic, because it has to interact with the light. The semiconductor has to interact with the light. At the same time, the semiconductor has to interact with the electrolyte also. So you need to have a high interaction volume for both electrode, solid and liquid, and solid and the light. So this is quite challenging. So what we designed a structure, a nanorod structure, which having a type 2 semiconductor heterostructure. What I mean by type 2 semiconductor heterostructure, for example, here an exciton formation happens, electron will come to this level. So the electron hole recombination will not happen. Exciton will not get again form a combine and then form a light. So this will not happen. Electron hole separation will happen in type 2 semiconductor heterostructure geometry. So that's why we afford a photocurrent. That's the principle of photocurrent generation. Now, this photocurrent, not only that, the holes generated should actually host the lithium. For example, in this particular MOS2 MOS, the MOS2 has to hold lithium ions, because this is, since a layered material like graphite, it can hold lithium. Now, holes should be generated at the MOS2, otherwise the holes cannot get accumulated here and the oxidation cannot happen. So all these conditions need to be satisfied while designing a material, and we could found that in MOS to MOX such a strategy can be obtained, and we created such a surface structure type 2 semiconductor having both MOS2 and MOX. And we showed that, and I don't have time to explain all these things. Somebody is interested, I can go and detail it. But we showed that the photocharging happens for several hour times and cycles. Now another fundamental question comes here. When the, as I mentioned, when it get intercalated with the lithium, phase transition can happen. One of the earlier slides I mentioned, a slight strain into the sulfur plane can transform a semiconducting MOS2 to metallic MOS2. And we could see, as I told you, spectroscopically using Raman, you can see the phase formation also, that particular phase formation. And when you charge it, the reversibly that phase got disappeared and it goes back to the other phase. Now the question is, when you do this MOS2, small amount of lithium itself will metallize the MOS2. If you become metallic, then there won't be any more exciton formation. So somebody from Cambridge challenged this concept. A very famous scientist challenged this concept. This will not work. Then it was our duty to prove that this will work. There is fundamentally something else is happening, and we found that yes, when you form a type 2 semiconductor heterostructure like this, MOS to MO3, the phase transition can be delayed. It can hold almost double the amount of lithium otherwise it can hold before the metallization happens. So this we have proven, and theoretically we have proven, and we have shown experimentally also. If you have an MOS to MOX heterostructure, and then if you study the conductivity of that, the conductivity, the metallization happening in MOS2 is quite rather very slow, unlike in the case of pristine MOS2. So this is easy. When you look into this kind of application, you are also unraveling several fundamental things, and it was unknown to the semiconductor field that you can actually delay the phase transition of a semiconductor by this method. And it's very useful not only in batteries like what I showed now, photo battery, but also it will be useful in many other systems like photocatalysis, etc. Now we establish those who are in battery field, they may say that this is not a right, MOS2 is not a good cathode. Then we showed this is the real nice, the first cathode material people have demonstrated, that is TiS2, and it is found that even TiS2, this principle works. Not only that, this can charge the battery back also. While discharging the battery exposed to light, you can actually enhance the capacity. That means you can extend the life of the battery while discharging. So this is also quite nicely possible. We have demonstrated, and you can with almost 100% charge and discharge capacity, 100% Coulomb efficiency. We also investigated the role of light here. What all we found is that just one particular paper I'm just discussing in brief. If you have the right geometry for photocharging, without the degradation of the solid electrolyte interface, you can actually charge the battery back. But if you don't have the right photocharging mechanism, then you have the first solid electrolyte interface I mentioned, which has different components, which can get degraded, and this will affect the battery performance. So we even we have shown the Arduino based photocharging battery system, which can actually do the light based charging thing. So it basically what you are trying to say is that instead of electrically charging, you can develop photochargeable battery if the battery is not completely discharged. So several such concepts in principle by interface engineering can be developed. So this is one of the things I mentioned in the earlier thing. Not only solid liquid interfaces in battery or solid interfaces in electronics. Water structure itself, playing with the water structure itself is a very important thing. And I showed you that how important how important the tuning the water structure. This is what I told you in one of the slides. Since I don't have time, in 2 minutes I will stop. The thermodynamically, all these electron transfer reaction, hydrogen evolution reaction, carbon dioxide to carbon monoxide reaction, carbon dioxide to CH3OH, carbon dioxide to methane, all these reactions are very similar delta G, because delta G is equal to minus NFE. So the E standard potential corresponding to the delta G values. So they are all very close. That means that thermodynamically, all of them are equally likely possible. Now the question is that the number of protons, can you now control the number of protons and number of electrons here? so that you can control the kinetics and control the product. And we found that yes, it is possible. You can sometime break the hydrogen bond so that you can make the hydrogen evolution reaction mostly effective. So lots of hydrogen, so hydrogen proton will add a lot of protons, so it will form hydrogen. But if you limit the number of protons, and then you basically you can actually enhance other coupled reaction like a proton coupled electron transfer reaction. So for example, in carbon dioxide to carbon monoxide, if you was in gas, if you want to produce, you can control it just by adding some small molecules, where by creating hydrogen bonding. So making hydrogen bonding, all these water structure modification are not in bulk, only very near to the electrode surface. Okay, so it is important in different contexts. With that, let me conclude. Conclusions are, interfaces play a very seminal role in any energy management. I hope I could convey to some extent. With their understanding the interfaces, new concepts can be developed. As I showed you, can you charge a battery using light? So this was a fundamental question we asked, and we found that it is possible. Can we split water easily? We found that it is possible. Can we develop safer batteries? Yeah, we found, there are ways you can propose by understanding the interfaces, etc. So thank you for your attention, and all the entire credit goes to my students, whoever, and also a lot of collaborators and funding agencies. Thank you very much. I'm happy to address any questions if you have.
Thank you, sir. Before we conclude, we would like to open this platform for questions. So anyone have questions to share, you can directly ask by unmuting your mic, or if you prefer, you can put them in comment box too. Any questions?
Is there any questions?
If you have any questions, please share. If you want, you can also type in comment box too.
Hello, am I audible?
Yes.
Yeah, so like I had a question. So you were talking about the TMD semiconductors, right?
Yes.
Yeah, so my question is what at the end of the day, what actually, controls whether a TMD like ends up being a metal or like metallic or a semiconductor? Or is it just the, electron filling in the d orbitals? Is that alone what factors to this, or is there another factor based on the layers or interlayer coupling? Does it have anything to do with that?
Yeah.
It's an interesting question. So it's all about the d orbital arrangements is one particular answer, but the interactions, the interlayer interactions can also change. So what I'm saying is the monolayer to multi-layer can also change the band structure. So most of the time, the metallization, so-called metallization in these TMDs of high gap semiconductors are happening, the MOS2 etc. are happening by d orbital changing or modification at the d orbital levels, not by the number of layers. Because, for example, number of layers in MOS2 change, MOS2 will be happening, will only change the direct to indirect transition, not really a kind of phase transition from metal to semiconductor, etc. But at the same time, as I mentioned, you know, a 2H to 1T prime or 1T prime transition can change the band structure of these things even in the monolayer limit. So that's actually kind of this you know, interaction with a certain elements like lithium can actually permanently shift the slide the sulfur planes. So this will actually also change the way the orbitals are being arranged in a monolayer limit. So this is also one of the ways to make it from a metallic to semiconducting to metallic or vice versa.
Okay, sir. Thank you.
Any other questions?
Hello, can I ask one question?
Yeah.
Yes, sir.
Shivaji Reddy from faculty from physics department. Actually, we have shown two beautiful images of TM images of MOS2, in which one of the one of the cases both the sulfurs are in the same line when you look at it from the top, and in the other case they are not so. So that has something to do, anything to do with whether it is a metal or a semiconductor. Whether that decides whether it is a metal or a semiconductor.
Can you ask the question again? I mean, I didn't understand which thing you are talking about. Let me show to
You
the
have
slide
shown,
again.
yes sir, you have shown two TEM images in which in one of the images sulfur presence was visible, and in the other image not this one, sir, initial ones.
All right. Oh, okay. I understand. Okay, this one. Yeah, this one. Yeah. All right. Okay. Yeah. So what was the question? Yeah.
Is it that one of these two is a metal and the other one is metallic and the other one is a
So this particular case, this 1T is actually not thermodynamically stable. It's 1T prime, so distorted octahedron. So this is basically a metallic, and this is basically a semiconducting in nature.
Okay.
So this is what I told you. This phase transition occur with the shift of the sulfur plane, and which actually changes the hybridization, and which the orbital hybridization, and which actually changes the d states of the metal.
Okay, sir. From the experiment point of view, how suppose I want only semiconductor phase, I don't want the metallic phase. How to control that?
So basically, the monolayer MOS2 is the 1H phase is thermodynamically stable. So you will end up most of the time you end up with a semiconducting MOS2 when you go to monolayer, just a pristine MOS2. Yes, the 1T or 1T prime phase is not very easy to get and stabilize it unless until you introduce some strain or so. So most of the time it will be semiconducting only.
Okay. Okay, sir. Thank you very much.
Sir, there is one more question in comment box from Mr. Sridat. While fabricating semiconductors, we need a NM level precision, and it's related to interface engineering. So how such a precision is achieved in industry?
Yeah, so industry, this is what I told you, right? You are actually creating a flat band near to the metals, near to the semiconductor by ion implantation also. So you basically what you are trying to do is that this barrier width, it's all decided by the number of carriers in the semiconductor. So this, since it is not a degenerate semiconductor, this barrier width is quite high, so you cannot have a field emission. So at the junction, what they do, the junction of metal and semiconductor, they do ion implantation to make it a degenerately doped semiconductor, and so that the barrier width is quite drastically reduced, so that the field emission can happen. So this will be metallic contact between metal and semiconductor. So this is the way silicon industry currently is doing. So typically by, I think, aluminosilicate formation also. I think aluminum is the most used metal for such implantation, etc. Is that clear?
Mr. Sridath? Yes, sir, he texted. Is there any other questions? Anyone? If no, I think we could wind up. So, on behalf of Bhauthiki and NITC, we extend our heartfelt gratitude to Dr. T.N. Narayanan for delivering such an insightful talk on interface engineering. Your expertise and perspective have provided our students and faculty with a deeper understanding of this fascinating area of research and its relevance to modern science and technology. We could also like to sincerely thank our head of the department, Dr. Vari Shivaji Reddy, for his constant encouragement and guidance, and our faculty coordinator, Dr. Nadeshan Yogesh, for his unwavering support in making this event possible. Their valuable involvement has been instrumental in strengthening Bhauthiki's efforts in creating a vibrant scientific culture at NIT Calicut. Also, we thank our audience for attending this session. We hope the session sparked curiosity and look forward to seeing you in our upcoming lectures too. Your presence meant a lot to us. Once again, thank you all.
Thank you very much.